this project is to design the foundation for this structure. This is the structure footprint right here, and you can see that we're going to have two options. We're going to have 9 columns. So these are the columns, 9 of them there. Or the same structure, but we might have 36 columns. So part of it is we're going to decide which foundation works better. But you can see that there are, I'm not going to go through all of them, but you can see that there are 36 columns there. So it's 80 by 80, 80 by 80. So we can have this situation or this situation. So either the 9 columns in our structure or 36 columns in our structure. The weight of the structure is 30 million pounds, and we are going to consider both what we're calling type 1 and type 2 foundations. So if you remember, a type 1 foundation is what? It's a mat with a basement, but this mat may also have piles underneath it. So that's the type 1. So the type 1 is an entire mat, and there may be piles underneath it. Whereas the type 2 foundation, what we're calling a type 2 foundation, is going to have individual columns with basically footings and piles underneath each individual column. So I have a bunch of columns. I may have piles underneath each column. It looks like that. So we need to know how many columns we're going to have for the type 2 foundations. So these are the parameters for this particular design. Now, the type 1 foundation is easy to figure out what is our Q, essentially. And that's simply going to be, because the type 1 foundation is the big mat, it's simply the 30 million divided by 80 squared. So 80 squared, 80 squared. And that gives us a Q of 4687. On the other hand, if we have a type 2 foundation with 36 columns, for instance, then what? Well, we have, if you remember, all of these columns here are considered center columns. And, so we have the tributary area for the center column. So if we break this into tributary areas, we're going to see that we have, for instance, that is a corner column, that is an edge column, this is a center column, and each of them have different tributary areas. And so the tributary area for the corner column is there. The tributary area for a center column is there. And the tributary area for an edge column is there. So, we know that given that there are 6 columns here, and the spacing between columns then is 16 feet. So, the spacing between columns is 16 feet. And that means that when I figure out the tributary area of, for instance, a corner column here, that this is 8 feet and this is 8 feet. So the tributary area for a corner column is 8 feet by 8 feet, which is 64 square feet. Now, I'm not going to go through all the calculations, but that means that a center column is 16 by 16, which is 4 times that of a corner. So a center column takes 4 times the load of a corner column. And so all of these center columns, in a sense, count as 4. So I have 1, 2, 3, 4 times 4. I have 16 center columns, and that's equal to 64 corner columns. And the edge column is worth 2 corners. So, and how many edge columns do I have? Well, I've got, all of these are edge columns. All of those are edge columns, edge columns, edge columns. So I also have 16 edge columns. And that is equivalent to 32 corner columns. And I have 1, 2, 3, 4 corner columns. So that's 4 corner columns, which is 4 corner columns is 4 corner columns. So the end result is, if I add all those together, I get the equivalent of 100 corner columns, which means that the load on a corner column is going to be what? Is going to be the 30 million divided by 100. And that means a corner column has 300,000 pounds on it, whereas an edge column has twice that, 600,000 pounds, and a center column has 4 times that, which is 1.2 million pounds. So you can do something similar for this particular situation. I'll let you do that on your own. But these are the loads associated with the 36 column building. What is the, okay, this is the soil profile. And I'm showing 2 situations here. I'm showing the type 1 foundation and the type 2 foundation for our structure. So the type 1 situation, and I'm going to tell you right in advance, this is going to be case 1.5. The type 2 is case 2.9 is what I'm showing. So we're going to have a bunch of different cases, but this is 2 of the cases. So what is this case 1.5 here for the type 1 foundation? Well, here's my structure. It's got a basement. The basement is 20 feet. And then I have piles underneath the structure that go down to 45 feet. That's one of our cases that we're going to consider. If I have, with my type 2 foundation, I'm showing again I've got a 20-foot basement, and then the piles, of course, go down to 45 feet, but now I have individual columns supported on piles, and I have this pile cap here. It's the pile cap footing, however you want to look at it. So rather than have a large mat here, I'm going to have, individual, can't show them all, but they're all going to be like that. So under each column, we're going to have a pile cap with piles. The soils themselves, I've got a gravel layer, silt layer, sand layer, clay, gravel, silt, sand, clay, bedrock. So we have quite a number of different soils here. And you can see all the boundaries here are given. And so that is our bedrock is at 230 feet. You can see basically what we have. If you look at this, what do I have? I've got the trouble areas, of course, of the silt layer, that clay, silt, and clay. And between those layers, we have, there's a thin layer of sand there. There's some gravel on the top. There's a little bit thicker layer of gravel there. A little bit thicker layer of sand there. So a lot of silt and clay. And interspersed, I have some thinner gravels and sands. And what we're looking at here is, for instance, we're putting these piles down here. We're trying to get them down to the gravel. And then another situation, we're going to take piles down to the sand. So those are the cases we're looking at, we're going to look at. And of course, we're going to do, this for both the type 1 and type 2 foundations. These are the soil properties, so there's the layers, and you can read across what these are. We may or may not use all of them, but they're all there. Then this is these are strength information. This is, so what is this? Here I have SU over sigma prime I in the clays and silts, but that's at the OCR given, so that's NC 1.05, 1.11, 1.81, and that's plotted here. So in other words, that's 1.0, 0.35, so I come in here, oh, that's right there. And then this line gives the strengths at different OCRs. Similarly, if we look at, let's take that one, 1.81, 0.75. So I come in here at 1.81, 0.75, that's layer 8, and that gives us this line. So that's how you interpret that particular graph. Okay, so we are going to look for differential settlement less than 1 over 300, and we're going to design the type 1 foundations for the soil profile and properties given, and design the type 2 foundations for the soil profile and properties given, and we're going to consider both 9 and 36 columns. The cases for the type 1 foundations, we're going to have 7 different cases for the type 1 foundations, and this is the details here. So we have the different cases. We have the type, which is a mat with no piles underneath it. A mat basically with end-bearing piles underneath it. So in this case, for the first two, I just have the foundation depth, meaning we're going to put the mat at 20 feet or 42 feet with no piles underneath, or we're going to have the mat at 45 feet. Oh, sorry. The no basement, the mat at the ground surface. So these two, the mat is at the ground surface, but I have piles down to 45 feet or 110 feet. And then I've got a basement down to 20 feet with piles down to 45 feet, a basement at 30 feet with piles down to 45 feet, a basement at 40 feet with the piles down to 110 feet. So lots of different combinations with part one, with type 1 that you want to look at. Now, if I look at this first one, it's just a mat with a basement depth down to 20 feet. If I look at that, then what do I see? Well, that's basically this situation, but no piles. So there's no piles. If there are no piles there, then what soils are being compressed? I have this layer of silt. So that's layer 2. I have this clay layer here. That's layer 4. I have this silt layer here, layer 6, and then I also have this clay layer here, layer 8. So I have all of these layers that can get compressed, 2, 4, 6, and 8, which means you have to analyze each of those layers. So when you do your calculations, you're going to have 2, 4, 6, and 8. And you have to look at points of interest in each of those layers. So similarly, I've written down here which layers you need to consider for each case. So for case 1-2, you've got to consider 4, 6, and 8. You can draw these out. Then you need to consider 6 and 8 for 1, 3. And you can see the rest of these here. Then something similar for the type 2 foundations, but I've got 12 different cases for type 2 foundations, and they depend on the number of columns, 9, 36, 936, 936, 936, etc. And we're going to have the pile cap width. If I have 36 columns, my pile cap width is going to be 11 feet, meaning that's sort of the width of the footing. And for these first ones, there's no basement. But the pile depth varies. I have 30-foot piles, 45-foot piles, and 110-feet piles. For the next ones, I put in a basement of 20 feet. So here the basement is 0. Here the basement is 0. Here the basement is 20 feet. That's how those groups differ. And then these are the layers that are being compressed. Those are the ones you need to consider when you calculate your settlement. Here's an example. So I'm going to do case 1-6 for you. And so you have to fill out 2 pages. So this is 1-6, but this is layer 8. Okay. So, oops. So this is case 1-6, but for layer 6. Let's just look at it. So in other words, for case 1-6, we have a foundation type 1. That's our big mat. The foundation depth is 45, but I have basement depth of 30. Foundation width is 80. And we're considering layer 6, which gives us a point of interest at 82 feet, and the thickness of that layer is 56 feet. So what does that say? Let's look at layer 6 with foundation depth of 45 feet. So here's our foundation depth goes to here at 45 feet. So that means that I don't consider this layer here. That silt isn't a problem for us, and this clay is not a problem for us, but this silt and this clay are. So that's layers 6 and 8. And we know the pressure bulb, goes, the width is 80, so the pressure bulb is going to go down 160 feet. I didn't draw that very well. Pressure bulb is going to go down 160 feet, so in other words, this is 2B, which is 160 feet. So that's going to come down to, this is 205 feet at the base of that pressure bulb. So we get a point of interest in the middle of this silt, and then we get a point of interest, not at the middle, but a little bit above. I'm not going to go through the calculation of how to get that point of interest. You already know how to do that. So let's just look at the numbers. You're going to fill out tables like this, and so what do we start with? Well, this is done. This is before the structure is built. So I want to get what are the stresses in the soil before the structure is built. So let's start there. So if I add up the sigma V, at my point of interest depth is 82 feet in layer 6. That's the center of layer 6 at 82 feet. And what do? I've got to add up my sigma V just by, you can do this, just adding up all of the stresses from each layer. And then there's the pore pressure at that depth using the water table. And so my sigma V prime is simply sigma V minus U. That gives me my sigma prime I. The OCR for layer 6 is 1.11. And 1.11 times that gives me 5317 for my sigma prime P. So that's before the building is built. So before the structure is built. So I've got my sigma prime I, got my sigma prime P before anything is built, and then now I'm going to go through my typical analysis. This is so it's a type 1 foundation. I've already done some of these calculations for you, being that I have my weight is 30 million and the area is 80 squared, which is 6,400. So P over A gives me Q. So take those two, that gives me that one. And so that gives me the 4688. And then my Z is what? The Z is the distance from the point of interest depth, so that goes there. And then the 45 is where? Well, that's my foundation depth is there, so that gives me a 37 for that Z. The B, this is a type 1 foundation, type 1, so the B is what? The full 80, full width. So we can get our Z over B here. Now, as you know, now remember what we're looking at here. We're looking at the center, we're looking at the edge, we're looking at the corner. And when we do our, this is a little bit of a trick, the Z over B is what? I've got to divide that by 2 there, if you remember. So it's 0.463 divided by 2 because it's the corner. And so I get my pressure bulb factor by looking at my pressure bulb. I look at the center of the pressure bulb. There's the edge of the pressure bulb. And then this is the center of the pressure bulb divided by 4. So I take this Z over B. In other words, I look at my pressure bulb at 0.231. Below the center gives me a 0.93. But then, so I look at the pressure bulb, I get that number, but then I have to divide it by 4 because it's the corner, if you remember that trick. So these give me my pressure bulb factors here. And then I simply take my pressure bulb factor times my Q, and I get these values here for my delta sigma V. That gives me what's going on with the piles. Well, the basement is, now we're going to do the basement, and the basement is what? Well, I have to figure out how much soil is being, the weight of the soil removed. Well, the rate of the, you can look at these numbers, but the weight of the soil removed, and you can calculate that out. You take the volume of the basement times the unit weights of the soil, and I get 19 million pounds of the soil removed. The area there is still the 6,400, and so P divided by A gives me Q, and there's my Q for the basement. And now what? Now I'm looking at the basement depth is what? Is 30, so that goes there, and then I get my the depth of my point of interest is 82. So 82 minus 30 gives me 52. for my Z for my basement. That's the Z for the basement. Then the B is 80 again. And what do? We do the same trick. I get 0.65. Then that's Z over B there, but then I have to divide by 2 to get that one because it's the corner. And then I read off the pressure bulb. This is the pressure bulb below the center. This is the pressure bulb below the edge. And this is below the center. I get 0.88 for that Z over B below the center, but then I have to divide it by 4. And I get the 0.22 here. So again, I take this pressure bulb factor, I multiply it times that, and that gives me these. And then, of course, I have a negative sign because it's the basement. We're removing the soil. So we are removing the load, so this has a negative sign. So I have center, center, and this is the center, so what do I have to do? I have to take the 3469 minus the 1636, and those two values give me that. And I have the edge, so 1922 minus 1041 gives me that. That gives me my delta sigma V. These are my delta sigma V's that I'm calculating out. And then, of course, the corner, 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 corner. I take these two right there. That gives me my delta sigma V. And then I have my sigma prime I here. So I take my sigma prime I plus my delta sigma V. Gives me that value. And I have my sigma prime I plus that. Gives me that value for my sigma prime F. And then that plus that gives me that. So I have my sigma prime I, I've got my sigma prime P, I've got my sigma prime F. I can take all of these, so this goes, that's the first there on my figure. The sigma prime P will go here. And then I look at my sigma prime F, where does it go? Well, my sigma prime F, 6623 means I go past the sigma prime P. This one goes past the sigma prime P, but this one, it doesn't go past the sigma prime P. So when I calculate out my strains, this one I have both parts. This one I have both parts. This one I only have the first part. So you can look at those numbers. We've done this many times, so I'm not going to go through the details. And then I have my H is 56 feet. That's the thickness of the layer in this case. I multiply, here are my epsilon V's times this is going to give me these values right there. So I get this is the delta H for this layer, layer 6. Okay, so I'm getting 1.76 feet below the center of my structure, 0.666 below the edge of the structure, 0.171 below the corner, but just for layer 6. Well, I also have to do the next layer, which is layer 8. I'm not going to go through this in as much detail, but basically it's the same calculation, and so same thing in this particular case. My OCR is 1.81, which means that in this particular case I have a very high sigma prime P, and I never get there. So I'm all, in this particular case, for this layer 8, I never go beyond the sigma prime P, which gives me much less settlement beneath the center, edge, and corner, because yeah, because of that. Okay, so now I need to put everything together, and so that, again, we're still on case 1-6, and I have to add these. So my center for layer 6 gave me 1.76 feet. We just did that for the edge. Layer 6 was 0.666. The corner for layer 6 was 0.171. Okay, so there's my, that's just what we just calculated. And for layer 8, we calculated these numbers beneath the center, edge, and corner. So to get my total settlement, I have to add these two to get my total. There's no layer, we didn't have a third layer. We only had 2 layers we had to consider here. So I add these two and get that. I add these two and get that. I add these two and I get that. Now, so now I get my numbers for my settlement. These are my settlements beneath the center, edge, and corner. And now I have to check out my differential settlement. My differential settlement, then I do the center to the edge, the center to the corner, edge to corner, and what we find is that you can see the numbers here. You can see that we get the center is 1.79 right there. The edge is 0.689 right there. I subtract them and I get 1.1. So that's the differential settlement row for center to edge. The distance between the horizontal distance is 40 feet. Well, how do I know that? Because my footprint, this is 80 feet, and the center is here, the edge is here. That makes that distance 40 feet. So I can then compute rho over L. I get 1 over 36, which fails. And we do the same thing, center to corner, edge to corner. You can look at that, and in this particular case, all of them fail. The only trick here is the length from center to corner, because here's my structure, there's my center, there's my corner. I have to get that length L, and what is that? Well, I use the Pythagorean theorem. This is 40, that's 40. So it's the square root of 40 squared plus 40 squared gives us the L. So that's the only little trick. But they all fail, which means overall the whole thing's failed. Well, even if just one of them fails, the overall is going to be fail. So this foundation does not work. Okay, so what we've learned from this is that with a foundation depth of 45 feet, a basement depth of 30, type 1 foundation, it doesn't work. We can't build that. It's too much differential settlement. So that's not going to work for us. What I can do now is look at, well, so now this is an example of case 2-2. So in other words, this is a type 2 foundation. So, and in case 2-2, you can look at the numbers given. This is foundation depth is 30 feet. There's no basement. The foundation width, that is the pile cap, is 11 feet. That was given to you. So that's going to be 11 feet. Now I'm going to look at only layer 4. Why am I only going to look at layer 4? Well, because my the foundation width is 11. If you remember, our foundation depth is 30. So our pile cap so in this particular case, we're going, oops, I don't know exactly how, yeah, maybe it's like this, I'm not totally certain, but it goes like that, and then this distance is only 11 feet. Well, that means our pressure bulb goes down like that, which is this distance is what, 2 times 11, which is 22 feet. So this is at 30 feet, 30 plus 22, and the bottom of that is almost there, is 52 feet. That means the pressure bulb only goes into this clay. It doesn't touch that silt. It doesn't touch that clay. So we're only looking at layer 4 here. So we only have layer 4 to consider in our settlement calculation. That's one of the advantages of building this smaller foundation, is that the pressure bulb does not take the load deep. So when we do our calculation, we only need to consider layer 4. The point of interest depth, you can figure that out, is 41.5. That means the thickness we're considering is 7. And then this is what is there before the building is built. So that you can do. You've done it a million times. Now what do? Now we look at the load of each column. I look at the load of a center column. We calculated 1.2 million. I look at the load on an edge column. It's 600,000. I look at the load on a corner column. It's 300,000. The area, I'm giving it to you that the foundation width is 11 for these, so its area is 11 squared, which is 121. I take P divided by A. That gives me the Q. And the Z is what? 11.5. How did I get that? Well, the point of interest depth is 41.5. That's 30. So that's going to be 11.5 there. And the B, the width is 11. And so now I get a Z over B. I just take those straight, 1.05. And now I read the pressure bulb beneath the center of the pressure bulb, center. For all of these, it's below the center of the pressure bulb when I have a type 2 foundation. I don't do the corner trick anymore. And then I take the pressure bulb times the Q. It gives me these values right there. So that gives me my sigma V, delta sigma V. I have my sigma prime I, I've got my sigma prime P. And then I have my delta sigma V. It's here. I just translate them. And I take this plus this, gives me these numbers here. And so I now have my sigma prime I, my sigma prime P, my sigma prime F. I go take those values, put them all here, and here, and here. In this particular case, we can see that we go past the sigma prime P, so I have to use both lines. And so there's my calculations of delta of epsilon V, and then my H is 7. Multiply it times those two, and that gives me my delta H. And then I do the same sort of thing. I look at this. So I have my delta H. This is final number because I only have to consider one layer here. So these are my settlements beneath the center edge and corner. And then I do the same calculation, but now I don't have anything here, I don't have anything there, so I only have one layer. So there's the calculations we just did, there's my total, and then I go back and I do my center to edge, rho over L, center to corner, rho over L, edge to corner, rho over L, and what do I find? 1 over 90.6, 1 over 56, 1 over 136. Again, they're not 1 over 300, they're bigger than 1 over 300, so that fails, that fails, that fails. Overall, that fails. So we've done 2 cases, I've done 2 of the cases for you, and in this particular situation, both of them fail. So these don't work. We can't build these. So that's why we try other cases and see if it works. So these are blanks. I'm giving you these. You can print them out, fill them in, do it for all of the cases, and then when you're done, you summarize them here. You write down the basement depth, the pile depth, and whether it passes or fails. So fill out this table to figure out, to list everything that you've done, and then once you've done that, I want you to put together some costs. So this, you can read this in detail. This is self-explanatory, but I'll look at it. It says compute the cost of concrete and soil removed. So all I want you to do is figure out the concrete cost and the soil removed cost for each of these and try to get an idea of which one is the most cost efficient, but only consider the cases that pass, okay? So I've listed a number of these. You have to decide how many of these passed, but you list only the cases that pass, not all of them. And you summarize them: the basement depth, the pile depth, the number of columns, the pile cap width. This will guide you to figure out what's the volume of the concrete. And these details tell you what to assume with regard to these dimensions. So in other words, we're going to assume that each pile is 1 foot by 1 foot by the pile length. That's how you get the volume of the concrete for the pile. So they're 1 foot. They're not 1 foot. 1.5 foot by 1.5 foot. 1.5 feet by 1.5 feet. In other words, they're 18-inch piles, and you take the length of them. You're going to assume that the concrete costs $60 per cubic foot. And now for the mat and pile caps, you're going to assume that the concrete is 3 feet thick. So you got a thickness of the concrete for the mat and the pile caps. And when I have 9 columns, you're going to assume that there are 25. So this is type 2 foundations. Okay. So when you have 9 columns, assume there are 25 piles under each column. Type 2 foundations. When you have 36 columns, assume there are 9 piles under each column. For the type 1 foundation, where the piles go under the entire mat, I want you to assume there are 400 piles under the entire mat. So that's going to give you the number of piles. And assume that the concrete cost is $60 per cubic foot. So you're going to get the volume of the concrete and then 60 times $60 per cubic foot. And then you're going to get the soil removed. For the cases with a basement, assume that the cost of soil removed is $15 per cubic foot. So you just take the volume of the basement times $15 per cubic foot to get the cost of the soil removed. And this guides you. So you got the case, you got the basement depth, the pile depth, the number of columns, the pile cap width, pile cap volume, pile cap or mat volume, and then the total number of piles for each one, the total pile volume, and the excavated soil volume by figuring out the volume of the basement. So, and then the soil cost is simply times $15 per cubic foot. The concrete cost in millions of dollars, I multiply by $60 per cubic foot, and then you add those two together and you get the total cost. Okay, so that is this part of the project. Fill everything out in these tables. Okay, almost.